In general, radio waves in particular, as waves versus particles. I'll talk about a little about the history of quantum mechanics and use the two-slit experiment as an example. I'll talk about a famous paper by Einstein, Podolsky, and Rosen called the EPR paper, and what that has to do with quantum entanglement, what quantum entanglement is. I'll talk about some of the alternate interpretations of quantum mechanics, including the Bohmian mechanic interpretation. I'll talk about Bell's theorem and how we test quantum entanglement to verify that it's actually there. And finally, I'll finish up by talking about applications, including a little bit about quantum computing, quantum communications, and maybe some quantum applications for amateur radio. So to begin with, talking about waves or particles, we can go all the way back to the 17th century and look at Christian Huygens and his wave theory, about Isaac Newton and his ray or particle theory, and Thomas Young and his wave theory. So let's start with Christian Huygens. He came up with the idea that every point in a wave front becomes a source for successive waves going forward. It's called Huygens' principle. And he used that to understand and analyze situations like refraction on the left and propagation, diffraction through a circular aperture on the right. Now, at about the same time, another physicist who's pretty well known, named Isaac Newton, did a lot of fundamental work in optics. And he had a completely different point of view. He thought that light was rays, physical objects that were traveling along discrete lines. He wrote a whole book, a treatise on optics, advocating this. However, at the same time, he identified what come to be known as Newton's rings. You can see this on an oil slick, for instance, with different colors. This is if you have a spherical mirror on a flat surface, you'll see bands where the light is dark and light and dark and light, where it's constructively and destructively interfering. And he noted that, and although he thought that light was a physical object, he recognized that it had periodic fits of easy and difficult propagation. So, and when he talked about the distances over which those fits took place, he basically came up with the exact wavelengths for optical light that we use today. So he had an interesting combined particle and wave theory. His view really was particles with wave-like properties. Well, most people accepted Newton's perspective of light being particles for another century or two, until a really brilliant physicist, Thomas Young, came around. And he pointed out if you have two sources and they interfere with each other, you will get an interference pattern. When people did those kinds of experiments, they saw light is behaving like a wave. Light from two sources will generate an interference pattern. Well, it really came down about a decade or so later. The French Academy decided to have a competition to see who could best explain light. And a very young physicist, Augustin Jean Fresnel, decided to participate. He wrote up his wave theory of light. He submitted it to a very skeptical committee, the head of which was the famous physicist Simeon Poisson, and Dominique Arago was also on the committee. And Fresnel gave them his wave theory, and Poisson took a look at it, and he said, But Monsieur Fresnel, if I look at this calculation, you are telling me that if I have a circular shadow, there will be a bright spot in the middle of the shadow. And that's nonsense, because we don't see bright spots popping up in the middle of a shadow. So your theory is nonsense. Arago heard that, kind of scratched his head and said, let me take a look and see. And what he found is, sure enough, if you take a little tiny circular dot and you shine a light on it, you will see a little tiny bright spot show up in the middle. Now, this is a more modern calculation of what it would look like, and you can see the intensity across the center of that. But yes, the waves add up constructively at the very center of that circle, proving or supporting Fresnel's theory. You can look at it in a cross-section too. On the top, this is what the intensity looks like for light behind a circular disk. So you can see that bright spot along the center axis of the circular disk, if you get the dimensions, the size, and the wavelengths correct. On the bottom, That is what it looks like for light going through a circular aperture, where you're getting the light adding up constructively and destructively to give rise to the pattern of light that you see going through that circular disk. Now, if we take a look at this from a more modern perspective and look at the actual energy flow in the light, we get patterns that look like this. For the circular, the shadow behind a circular disk, we have the top pattern, where you can see all the light above and below the disk and how the energy curves and converges to form the spot in the middle under the influence of the waves that are diffracting around the edge of the shadow. Or you can take a look at the waves as they interfere for light going through a circular hole. Well, that was the state of the art for understanding optics, in particular, a branch of electromagnetism, until the early 20th century, when people started looking at the structure of the atom. And one of the first major discoveries that was made was by Niels Bohr. He came up with a Bohr model for the atom. And that Bohr model, if you applied to hydrogen, would give you a very accurate replication of the observed spectral lines. And as people further developed it, they came up with Heisenberg and Schrödinger developing matrix and wave theories for how the hydrogen atoms put together. You get pretty patterns for the different hydrogen orbitals that look something like that. It's a more detailed look at that. Now, the thing that was really confusing about quantum mechanics was, even with the wave function of quantum mechanics, it seemed like the wave would propagate throughout space, and only at the moment you had a detection of some kind does the waveform collapse. So if we go back to light passing through a little tiny aperture like here into this semi or hemispherical chamber, the light, we don't know exactly how it diffracted through that hole. It could be anywhere in the chamber, and only at the moment that it converges and we detect it at a point P does the waveform collapse throughout the chamber and giving rise to our measurement. Well, that was kind of confusing because it suggested that all of this was happening simultaneously. Well, there were a number of interpretations of this. The most common interpretation was due to Bohr at his Copenhagen Institute, the Copenhagen interpretation, that all of the states, basically all possibilities are simultaneously playing out until the moment of measurement, where the waveform collapses at the moment of detection or observation. Well, there was another later theory, many worlds, that argued, well, everything happens. It's just we see what happens in our universe, and there are many parallel universes where all of the other outcomes are happening. And there are some people who like that approach. Well, there was a third approach that argued that the quantum fields served to guide the photon on a particular trajectory, that all the time it was following the path to that point P where it was measured, and it was only on detection that we observed it, that it was more, the wave function was telling us more about our state of knowledge and not anything metaphysical about the particle being smeared all over space until it was detected. And you can see Heisenberg was a firm advocate of the Copenhagen approach. Well, Schrödinger really didn't like that, and he came up with an example to illustrate how ridiculous some of the Copenhagen ideas were, that's come to be known as Schrödinger's cat. He pointed out if you could stick a cat in a box with a radioactive material that has a 50-50 chance of decaying over the course of an hour, and then when it decays, a little apparatus rakes a vial of poison and kills the cat. So at the end of an hour, there's a 50-50 chance the cat is dead. So before you open the box, is the cat alive or dead? The Copenhagen interpretation would say, well, the cat is in a superposition of being simultaneously alive and dead until the moment you open the box and collapse the waveform and converge to one of the other solutions. Well, Schrödinger came up with that as an example of how ridiculous the Copenhagen interpretation was. A lot of the Copenhagen people took that as, yep, that cat is simultaneously alive and dead, and that's exactly how it works. Of course, the final word on the Schrodinger's cat experiment was by Schrodinger's daughter, who observed rather aptly, "I don't think my father liked cats."
And I don't think these days you're going to be able to hold up like that off with your feet all over.
Yeah, it'd be tough to get the permission to do that.
I was in Virginia recently, and there had been quite a town to pay for dog kennels for research.
Right.
Oh, those people just go crazy.
So don't do this experiment at home is what we're talking about. Okay, well, in 1927, there was a very famous physics conference at the Solvay conference in Belgium. And some of the most brilliant physicists all came together to discuss quantum mechanics. And at that conference, an idea was presented by this guy, Louis de Broglie. And his concept was that the quantum wave piloted the corpuscle, they hadn't called it photons at that point, around, and that's why he called it the pilot wave theory. Well, if we apply that to the two-slit experiment, we can kind of look at these different interpretations and see how they play out. The famous physicist Richard Feynman argued famously that the two-slit experiment captures the essence of what quantum mechanics does and how strange and unusual it is. It contains the only mystery of quantum mechanics in his view. What Feynman said, well, what happens is, and this goes back to that experiment that Thomas Young proposed, of two slits and the waves going through the two slits generating an interference pattern. What people discovered is even if we made this light very, very dim, so that we could say with a statistical certainty that there's only one photon traversing the two slits at any given time, we still see the interference pattern. So how can one photon, which you would presume has to go through one slit or the other, generate an interference pattern based on the other slit and end up landing in one of those interference maxima? So, this is what happens as you start measuring the individual photons as they are detected on the screen. They will pop up at seemingly random places, but when you start averaging the statistics, you'll find that they're lining up in the pattern of the interference maximum, even though you're only sending them through one at a time, very slowly. And this is the an actual set of experimental data obtained when you do something like that. So what I want to do is show you a couple of cool videos, if hopefully the internet connection holds and we can get these to play, modeling what happens through the two-slit experiment. So here, does not look like it's going to play for me. But here what we have is the probability cloud going through the two slits and generating those interference maximum. And if we were watching it, we'd see that probability cloud on one side of the two slits oozing through and spreading out and then generating those maxima and minima that you see on the screen. And that's interesting.
But the input side is one smooth blob in that experiment.
Right, exactly. And it's not wanting to play for it. I'll have to skip the other one. This kind of shows what happens. This is the intensity pattern that you'll see through the two slits. Now, in the pilot wave theory would tell you that what's happening is the waves are generating a family of particle trajectories. And then as any individual photon is going through the two slits, it's picking one of those trajectories to be guided on. So the waves go through both slits, they generate that interference pattern, and that serves to define a family of trajectories, one of which is taken by the photon when it goes through one of the two slits. So we have a photon going through one of the slits, and it works its way along one of those trajectories to be detected on the screen. That's what de Broglie tell us. Well, in the 1930s, a very famous mathematician, John von Neumann, came up. He wrote a book, The Mathematical Foundation of Quantum Mechanics. And one of the things he did in that was he presented what he argued was a theoretical proof that you could have no hidden variables, that the quantum mechanical description was as good as it gets, and that it was meaningless to talk about having actual positions of particles until they're actually detected. And that was generally accepted as putting a nail in the coffin of all the people who want to have these silly particle trajectories instead of just accepting the pure mystic wisdom of the Copenhagen interpretation. Well, a few years after that, we get into the Einstein-Podolsky-Rosen paper and the concept of entanglement. I'll talk about the paper, about entanglement and spooky action at distance, about a gentleman named David Bohm and his revival of the hidden variable approach and some of the reactions that had. And then I'll talk about John Bell, the theorem and the limits that he proposed, what they say about causality and locality, and I'll talk about how we test some of those limits. So Einstein came up with an example to kind of illustrate his thought of how the waveform collapses. It's called, it became known as Einstein's box. His idea was, okay, we have a mirrored box and we throw one photon inside this box and it's bouncing around. We don't know exactly where it is inside the box. Well, then we put a mirrored partition. We cut the box in two and we pull the two boxes apart. So we know the photon, we presume, is in one box or the other. And then we can take those boxes and put them arbitrarily far apart. We don't know which box the photon's in. The moment we look in one of the boxes and we discover either the photon is there or the photon isn't there, we're collapsing the waveform for the other box and finding the solution for that box too. So by knowing what's going on in one of the boxes, that tells us what happened in the other box. It makes perfect sense. So instead of reality being in some indeterminate state of being both occupied and empty at the same time, Einstein would say, no, that's nonsense. It's either in there or it's not. And when you open the box, all you're doing is resolving your uncertainty about whether that was the box that the photon ended up in. So he wrote...
Is that in the EPR paper?
That's before the EPR paper, but that was like one of the motivations he was thinking about as he and his collaborators wrote the EPR paper. And the basic idea behind this paper, he wrote it with Nathan Rosen, who you see there. I could not find a picture of Podolsky to throw up here, I'm afraid, but there's two of the three. What he argued was that quantum mechanics was incomplete and that you had to have hidden variables like, this box really does have the photon in it before you make the measurement. You couldn't, it didn't make sense to talk, and you couldn't have causality unless you had that kind of hidden variable telling you this box is empty, this box is full, before you make that measurement. Because otherwise, you're talking about having your box, or having the measurement on one box simultaneously collapse the wave function on the other box that could be arbitrarily far away and much faster than the speed of light. And that didn't make sense to Einstein because that defies causality and locality. And this is where the spooky action at distance pops up. Einstein wrote a letter to Born. You can see them both in that picture from the Solvay conference, arguing that he can't believe and take quantum mechanics seriously because it does not represent a reality in time and space free from what he called spooky action at distance. And that's the phrase that has been used to characterize it. Well, let's talk about entanglement. And I wanted to try to give a clear definition of what I mean and what physicists mean when they talk about entanglement. It's a phenomenon where the properties of two or more particles are codependent, with the properties of one being instantaneously affected by measurements made on the other, even arbitrarily far apart. So that Einstein's box case is kind of an example. We have two boxes, their properties, whether there's a photon in it or not in it, those properties are entangled. And when we make a measurement on one box, we're resolving what's happening with the other box. And that's a pretty simple and straightforward example. Well, yes?
Are you like an analogy, you're saying the boxes are entangled in
In that case, yeah, the box is the two boxes are entangled.
You don't have entanglement with one photon.
Well, in a way, you could say that the photon wave function is entangled because you have a wave function that says there's a 50% chance of a photon in each box, and then that is collapsing to tell you yes, it's there, no, it's not, the moment you measure one of the boxes. Right. Well, in the early 1950s, 1951, a physicist named David Bohm did a really masterful book on quantum theory. One historian or philosopher of science, Myra Beller, argued that it's the best discussion and description of what the Copenhagen interpretation meant. Well, as he was doing that and presenting this rigorous, well thought out explanation for how the Copenhagen interpretation worked, he began to have doubts. And he revived an approach for hidden variables, where particles had continuous trajectories. They're non-local in the sense that what's happening they're taking place over space, but completely causal and with trajectories just like the de Broglie pilot wave type pictures I was showing earlier. Now the reactions for that were kind of mixed. There was, and it's hard to tell because a lot of this is all second and third hand. These aren't the kinds of things physicists tend to put in their journals. But we have eyewitness reports that at the Institute for Advanced Studies in Princeton, Bohm was a Princeton professor, that J. Robert Oppenheimer held a seminar to discuss this Bohmian mechanics, and he wanted to put a stake through its heart and rule it out and prove it's impossible so that we can stop worrying about it and get on to doing real physics. And after they'd worked all day trying to come up with ways to disprove his hidden variable approach, one participant said, reported that Oppenheimer said, well, if we're unable to disprove it, we'll just have to ignore it. And there are a bunch of other anecdotes that various people have said. Things like Oppenheimer reducing a young physicist to tears by telling him, "No, we don't need to listen to your stuff on quantum mechanics. Bohr worked that out years ago. All these questions are settled. This is settled science, and we don't need to look at it anymore." Or another story about how Oppenheimer assigned it to a grad student to find the error because he was too busy to be troubled to refute something like this.
The number.
Yeah, and
Into a TA.
basically yes. And the grad student couldn't find anything wrong with it. And again, reporting that Oppenheimer said, "Well, we'll just not mention this again." So, some of these stories they sound almost too good to be true. And you have trouble believing that senior, serious, sober scientists would have these kinds of attitudes. And I'd have probably been in that kind of a camp also of, well, that sounds like someone's wishful thinking or someone's tall tale that they're telling to try to exaggerate this. And that would have been my position if I hadn't been a first-hand recipient or participant in one of these stories, because the professor who brought Bohm to Princeton was a professor named John Archibald Wheeler, a famous professor who was actually Richard Feynman's PhD advisor. And by the early 1990s, he was an emeritus professor at the University of Texas, where I studied. So I got to actually interact with him, and I asked him, what did he think of pilot wave theory? And his answer to me was, it's the screwdriver theory of the two-slit experiment. And I'd seen people make dismissive comments of it as I was reading in the literature, and I knew people thought it was unnecessary complication. You're just trying to put a mechanical scaffolding to satisfy your philosophical preconceptions, and you don't need it. You just use the Copenhagen interpretation. Just shut up and calculate. Just do the math. So I asked Professor Wheeler, because I knew he'd written famous textbooks on the details of quantum theory and measurement, and was a leader and well respected in this area. I asked him, so have you written some papers, or is there someplace I could go to see your more considered thinking on why this is the screwdriver theory of quantum mechanics? And Wheeler's answer to me was, well, I never really studied into that business, and I should so that I can see what's wrong with it. So that convinced me, yeah, there are a lot of physicists who had blinders on in terms of looking at ideas like this and taking them seriously. In fact, another famous physicist, Murray Gell-Mann, argued that the philosophical understanding of quantum mechanics had been long delayed because Niels Bohr brainwashed a generation of theorists into thinking it had been solved for 50 years. Well, backing up a little bit to the 1960s, a physicist named John Stuart Bell revisited this. He pointed out that von Neumann's proof had been disproven by Bohm. I mean, clearly the hidden variables theory that Bohm had was workable, and disproved von Neumann's supposed proof that it wasn't possible. But he took it to the next level. He peeled off one layer of the onion and found another more challenging and disturbing problem. What he pointed out is if you have a hidden variable theory, a theory that there's a discrete location or some other variables governing what's going on under the hood of the traditional quantum mechanics calculation, if you have a local hidden variable theory, it will have to disagree with quantum mechanics. And if it agrees with quantum mechanics, it will not be local. Let me talk a little bit about what that means, because it's it's kind of disturbing and confusing to wrap your head around. First, two concepts. Causality. That's the idea that every event has a cause, and that the cause has to precede the effect. So if there's a cause that gives rise to an effect, cause has to come before, and from a relativistic point of view, whatever effect happens, you have to have the speed of light time delay to get to where that effect occurs. A closely related concept is locality. That's the idea that they have to be nearby, connected in space as well as in time. And in practice, that nearby just means that propagation has to be no faster than the speed of light to have the cause give rise to the effect. Well, what Bell pointed out is if we have two entangled photons, there's certain processes, I'll talk about them in a moment, where you can get the simultaneous creation of a photon pair. And to conserve angular momentum, what you'll see is the polarization planes, it's random, there's no telling where they'll end up, but the photon going one way will be 90 degrees polarized relative to the photon going the other way. So if we imagine those little yellow polarization vectors going through a polarizing filter, like the filter here on the right that will only pass the horizontal polarization, or the filter on the left that will only pass the vertical polarization. What you find happening with these entangled photons is, well, they will either both be detected on both sides, or neither of them will be detected on both sides. They'll either both pass their respective detectors, where we've got the detectors at 90 degrees with respect to each other, or they will both not pass. So you have a perfect correlation in your measurements from one side to the other. Well, if we think of this as having a discrete, well-defined polarization, and we start considering different angles for our polarizing filters, what we see is a plot like this where we're expecting a curve in red, where the correlation between the two will go down. I think I truncated the scale, but it's +1 correlation, perfectly correlated at the top. The zero crossing is no correlation, it's random, there's no connection between the two. And at the bottom, they're perfectly anti-correlated. If you see one, you don't see the other. If you see the other, you don't see the first one. Well, you would expect with a model like this that as we're rotating them, the more we move them out of line linearly, the less likely it is they'll both be lined up. When we're 45 degrees aligned, half the time we'll see a coincidence, half the time we won't. It's random. And then as we move them to be co-aligned, so if they're both vertical or both horizontal, well, the photons are orthogonal, so we're not going to, we'll never make a detection on both at the same time. Well, quantum mechanics predicts something different's going to happen. Quantum mechanics predicts if we go in between here somewhere, that will actually see a connection between the two. So if we happen to have one of the filters aligned just a little bit off of the other, we will see more correlations than you would expect from a theory that says that polarization was determined in advance. And if we move a little closer to being aligned, we'll see more anti-correlations than you would expect. It's a subtle effect. I mean, you can see there's not a lot of difference between those curves, but we can actually set up experiments to do these kinds of measurements. There are some certain nonlinear crystals that are what's called birefringent. So if you send a light into them, it'll split into horizontally polarized and vertically polarized light. So you'll get, as a laser beam goes through, if you excite some of these nonlinear crystals, you will create an atomic excitation that decays to a ground state and generates an entangled pair of photons, just like we were talking about. So you can make these entangled photons using a process like this. And then you'll have horizontal pole going in one path and vertical polarization going on another path. And when you run them through a detector, the first experiment was along these lines was by Friedman and Clauser in the early 1970s. This is an example by Alain Aspect in 1982, and then a more recent example. What you find is that the quantum mechanical prediction is what is measured in the lab by these tests, where you have the polarizers on either side, you're measuring how many detections you get, and you're comparing whether you're seeing them at the same time. The statistics follow quantum mechanics, not local realism. Now, what Aspect did was let's see if I can get this. Yeah, he separated the detectors far enough that the speed of light from one measurement, where the setting you have on one detector could not possibly get to the other detector in time, and then was randomly having it shift one way or the other to make the measurement. So the photon at the other side has no way of knowing what the detector is doing on the first side, and not enough time for any sort of signal from, okay, I've set this to the detection on the other side, and the effect is still there. So very, very curious and confusing result. And then more recently, Alain Aspect was, Anton Zeilinger was doing similar kinds of tests over relatively large distances, many kilometers, and seeing the same kinds of effects taking place. So this is an example of a typical kind of experiment where we have a source, one of those crystals that's excited by a laser, decays and generates an entangled photon pair. We're looking at them through these two-channel polarizers that split the beam into horizontal and vertical polarization, and then comparing the results of the detectors on either side and looking for, then going back and comparing notes in our coincidence box. And that relationship seems to hold, that we're seeing somehow the nature of the measurement you make on one side is affecting the statistics on the other side faster than the speed of light. So there are a couple of interpretations that people have offered. Just going through the ones I've already mentioned. There's the Copenhagen interpretation, shut up and calculate, that's what happens. Abandon your notion of local realism. The hidden variables approach, but if Bell's theorem is correct, it has to be some kind of non-local hidden variables. And I don't know that anyone has come up with a suitable theory that would explain that. So a very confusing and perplexing result. So how does it work? Hidden variables, at least in a local sense, seem to be precluded by Bell's theorem and the limits that Bell set. People talk about somehow there being tachyons, faster than light particles communicating between one detector and another. I know one physicist who insists it's wormholes, that you have some kind of a wormhole from one detection to the other that are giving rise to it. There are others who argue that the great simulator who set up the universe, that's the way the math works out as the simulation is playing, and I mean all kinds of crazy explanations. But it does not allow faster than light communication, because what's happening is you don't know that the correlation exists and you can compare and see what's happening at the other side and get their data to see, oh yeah, that's correlated more than you would expect for this set of measurements. Now, in recognition of their experimental work, the three physicists I mentioned, Aspect, Clauser, and Zeilinger, ended up winning the Nobel Prize a couple years ago. So you may have heard that popping up in the news. Well, I want to conclude by talking about some of the applications for this kind of entanglement technology. The first is quantum computing. Conventional computers, of course, use digital logic where their bits are either ones or zeros. A quantum computer can act on in more of an analog basis using these entangled systems. An entangled bit is called a qubit, short for a quantum bit, and then do calculations based on the superposition or interference between those states. So there are certain kinds of calculations that quantum computing and quantum algorithms may be able to perform much, much faster and more efficiently than regular conventional digital computers. The challenge there is those qubits tend to be very fragile. It's tough to store them. They'll decohere and no longer be entangled if you're not very, very careful. So there are a lot of major engineering challenges facing the companies that are building these. But there have been quantum computers built with relatively small, I don't think much beyond double-digit numbers of qubits, and demonstrated some of the principles of this. Another concept that'll be near and dear to the hearts of us as amateur radio operators is using this for communication. Now, we're talking about sending individual photons at a time, so these are not high data rate channels. But where it comes in handy is by the nature of the channel. If you have a classical channel and we have an eavesdropper named Eve, appropriately, listening in, well, Eve can hear whatever's going on in that classical channel. Put her antenna up in the middle of your link and record your DX, and she's got copies of all your message traffic. And maybe you're using a code, but well, she's at least got a message of what you sent before you've done your decoding, and she can hope to try to crack it. She's got a copy of the message. In a quantum channel, though, because we're dealing with entangled single photon states, there's only one photon going one way or the other. And if Eve is listening in and detecting the signal on one side or the other, she's destroying the photon. So basically, the link's gone, and even if she were somehow able to capture, characterize it, it never got to the other side in the first place. So the idea is this could be used for sharing encryption keys. That if you had two users separated at a distance who were both listening to the same entangled photon source and comparing their correlations, if they set up their polarizers to have the correct polarizations, like 90 degrees out of phase with each other, they'd be getting exact copies of the polarization states and use that as their digital code, as an encryption code for sending messages over the classical channel. So it has a lot of promise for doing very high security, low data rate links. Of course, the challenge is with these that people are mostly looking at optical signals on optical fibers, or maybe near infrared through free space. The problem is that radio wave photons, the photon energy is linear with the frequency. So you can get reasonable energies for frequencies as high as the speed of light, or maybe even infrared, but by the time you're at the relatively lower frequencies of gigahertz or megahertz or down, there's not much energy in those individual photons. It's very hard, if at all possible, to detect individual radio photons. But there are some interesting quantum effects that do pop up that are within the range of amateur radio equipment. One is this hyperfine transition effect in hydrogen. Hydrogen atoms can get in a slightly excited state where the angular momentum, or the spins of the electron in the nucleus, are co-aligned. And then when they relax and flip back into having opposite angular momentum, the hydrogen atom will emit a signal at 1.42 gigahertz. And that's picked up by radio astronomers. A lot of times you'll see, if you send a radio wave of broadband radio signals through a hydrogen cloud, it'll excite those transitions, and you'll see a quiet spot in the spectrum where those frequencies have been absorbed by the hydrogen cloud to set up those excited states. So that is a quantum effect that you can detect in principle with amateur radio equipment operating at microwave frequencies. But the problem is the single photon entanglement requires frequencies that are unfortunately beyond the capabilities of the usual tools that are in the amateur radio shack. So I have talked about a little bit of history about waves and particles and quantum mechanics, about the EPR paper and entanglement, some of the interpretations like the Copenhagen interpretation and the pilot wave interpretation, and a little bit about entanglement, how we test entanglement, how confusing it is to see these extra correlations that suggest that we can't use a local realist model. And then applications including quantum computing, communications, and the possibility of doing some quantum applications in amateur radio. So what I want to do is, if you're interested in learning more on an advanced level, I really liked these two books. Peter Holland's book on the quantum theory of motion. It looks at quantum mechanics from that Bohm de Broglie hidden variable perspective. I also liked Franco Soleri's book, Quantum Paradoxes in Physical Reality. These are relatively advanced books. You probably would want to have some quantum mechanics background before diving into them. And I want to put a shout out for the book that I am currently writing, Fields and Energy, How Electromagnetism and Quantum Mechanics Work and Where Physics Went Wrong. I'm serializing that in weekly installments on Substack. If you go to etherzar.substack.com, you can subscribe. It's free. I mean, if you want to upgrade to a paid subscription, I'd appreciate it, but all the content is free and you can get the free updates. I've just been talking about how transmission lines work and the story of the telegrapher's equation up there. And I'm trying to convey the subject matter in an easily accessible style that you don't have to have a PhD to be able to follow and understand. So I'll conclude by advising you to keep calm and make physics great again. I'll be happy to answer any questions.
Please try to explain to us the many worlds hypothesis, and give me your opinion as to whether it really boils your gut.
There's a fundamental principle in inductive reasoning called Occam's razor, where you want to take the simplest possible explanation for a physical environment, or at least you want to consider it very seriously before going to much, 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 much more complicated explanations. The many worlds theorem I see as being one of those much, 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 much more complicated situations. I mean, what many worlds is saying is that at any given instant, uncountably many duplicate universes are being spawned because of subtle differences in, not just like the flip of a coin, but every little subtle atomic motion where that air molecule zigged this way instead of zagging that way. Boom, two separate duplicate copy universes. I mean, holy Occam's razor. I think that doesn't make a lot of sense. So that's my position on it. Yeah.
So the way you described Einstein's hidden box findings, that's exactly, that makes complete sense to me. And it sounds like that's been fairly well disproven. And so what is the reasoning for what's caused that to be?
Well, yeah, it makes perfect sense to me too. And what Bell's theorem says is that effectively, if we're looking at those polarization states, you cannot have a situation where the measurement outcome is predetermined by the state of the photons at the moment the pair is entangled or created. That there's some other process, some additional process going on that has to account for the additional correlation or anti-correlation that you're seeing when you make those measurements. So then the issue is, we can see that how you measure it on one side or the other has some kind of an impact. So is it some faster than light influence that's getting back and making that happen? Or is there some other theory that can explain that? So at the moment, it's a paradox. No one really understands how that works. But it's by looking at questions like that and thinking deeply about them and trying to figure out, well, what mechanism could be involved that we make progress. Yeah?
Could you roll back one slide, please? I missed snapping a picture of it. Thank you.
Sure.
That was the only question. Thank you.
Any other questions? Yes, in back.
The faster than light travel time requirement for communication to solve correlation of the spooky action at distance.
Right.
General relativity and reference frames would not apply.
There's a reason that Einstein did not like this theory. I mean, basically, yeah, it says everything we believe about causality and locality from relativity. We'll throw that out the window. We've got some weird, spooky action at distance at play here that isn't following the usual rules. Any other questions? Yes.
Do you believe that there is such thing as a wave function of the universe?
That is something that some people argue. My personal opinion is the wave function is really describing our state of knowledge more than it is. I'm in the hidden variables camp. So I think the wave function is describing our state of knowledge or lack thereof, our state of ignorance of a system that is then getting resolved by that act of measurement. So I think you can run into trouble if you start trying to take the wave function as being as having too metaphysical a reality. I'll leave it at that. Okay. Yeah.
So I've heard you talk before, and you have hinted in the past that there were deep connections between, say, Maxwell's equations and quantum mechanics, and maybe a lot of what is attempting to be explained by all of this spooky action at distance might simply be, electromagnetics, or at least part of it. Have you developed that any further in the?
I'm continuing to work on it and presenting my results on the Substack, week by week by week. Hopefully I'll have a good answer before I have to finish the book. But my argument, and I presented this at past Hamfests talking about my work. My argument is that classical electromagnetic theory describes how fields guide the flow of energy in a way that's very similar to how the Bohm and de Broglie pilot wave hidden variables approach suggests that quantum fields guide the motion of photons. It's a very similar picture. As near as I can tell, pilot wave theory, quantum mechanics is just the application of classical electromagnetic energy flow to the quantum realm. So again, I'm in the camp of thinking that Niels Bohr brainwashed a generation of physicists, and we're still suffering the consequences almost 100 years later. Yes?
I got introduced to sunspots and how, the sun's climate affects, ham radio communication. So I was kind of wondering how your take, if you've observed any of that about the sun weather and how it affects the physics.
That's not, there are people here who are a lot more qualified to talk about that than I am. But definitely, the sun is a variable star. It works in like an 11 or 12-year cycle of being more active and less active. And when it's more active, it has influences on the ionosphere. It'll change the propagation. And any ham radio operator who's done DX can tell you about the influence of the solar cycle and how difficult or how easy it is to make long distance connections. So I think, it's very well established that the sun has an impact on the ionosphere, and then through that to amateur radio communications. Sure. Yes.
It sounds similar to what Nikola Tesla has gotten into back when scalar energy is 0 point. Does this have anything to do with that? Some of his early theories?
Not really, but a full answer to that would take us into the next session here. So I think there are a lot of misconceptions on the whole scalar wave idea. You can express Maxwell's equations in a scalar format, but it's just a different mathematical representation. It's not giving you new physics associated with these scalar waves. It's just a different way to mathematically express the old physics. Now, I think Maxwell is not the last word in electromagnetism, and that there is possibly physics beyond that. I mean, there has to be to explain things like pair production, where if you get the intensity of a radio wave, and it becomes a gamma ray, and the energy gets high enough, that radio wave will split and form a matter-antimatter pair, and you'll have an electron and a positron. That's not described by Maxwell's equations. So clearly there's some limit where Maxwell's equations are no longer linear, and there's some new interesting things going on that deserve exploration and examination. Okay. Well,
Be at a much higher frequency.
oh yeah, that's a very much higher gamma ray kinds of frequencies. Well, I don't want to walk too far into the next session. I want to give our people coming after some time to talk. Happy to see you out in the hallway if you want to talk further. Thank you so much for your time.